Hello, good afternoon, everybody. All right, so let's get started with our lecture. We will have a midterm on Monday. So I haven't written it. I will be working on that all weekend. And yeah, so midterm number 2, it will cover lectures 10 through 17. So nothing that we covered on during this week, just the week before, so that it's covered by homework 6. And so that you know, to give you enough time to study and everything. So same format, same number of, roughly the same number of questions and so on. All right, so today we are going, well, actually, let me pause. Do you have any questions about the midterm? Or, I mean, it should be exactly the same format as before, so no. All right, so today we started talking last time about recent discoveries about black holes. In the last 5 years or so, there's a couple of Nobel Prizes that have been awarded to people who have made discoveries related to black holes. And I covered the first one, which was the discovery or the confirmation that our galaxy, the Milky Way, has a gigantic supermassive black hole in the center of it. This was discovered by a couple of groups, one led by someone at UCLA, the other one by someone at UC Berkeley. So it was pretty much a University of California discovery. And then today we're going to talk about two other discoveries that were very exciting. And then we'll start talking about what happens to me if I fall into a black hole. Let me see, I got a couple of questions about the exam. Yeah, okay, great question. So will you have 2 attempts for midterm 2? The answer is yes. And just be careful to know that you have to, if you want to take your second attempt, you need to take it, you need to have enough time to complete it. And last time I actually didn't, somebody asked me in the middle of the test, will I still get a whole hour? And I said, I actually don't know because I've never tried it. And it turns out, according to other students, they don't give you a whole other hour if you start it like toward the end of the test. You only have however much time you have between when you start and 5 p.m. So, you know, just be careful with that. But yeah, you have 2 attempts. If everything crashes, like last time for a bunch of people, everything crashed and you lost your internet connection, then of course you get that second attempt with the full hour, but then you have to contact me because we have to set it up. So, all right, that's all about the test. Same number of questions, yes, roughly between 25 and 30. Very good. So we will continue to talk about black holes. All right, so we talked about how a black hole warps the space around it. And according to Einstein's theory of general relativity, mass does that. And when mass is concentrated in a very, very small space, like it is with black holes, then it gets infinitely warped. And so, but when you're far away from a black hole, space is pretty flat. So if you're far away from a black hole, you're safe. You're not just going to fall into it. The problem is when you get very close and when you cross the event horizon, because when you cross the event horizon, then there is no way to get out, no matter what. So what happens? Are you guys still there? Am I still there? Yes, you are. Okay, great. Sorry. So I have my phone usually connected to the class too, so I can make sure what's going. I know what is going on, and somehow I got kicked out. Can you guys hear me? Can you see me? I don't know what's going on.
Yes, we can see you and we can hear you.
Oh, Gary, thank you. Thank you very much. Somehow my alter ego, which is my phone, got kicked out of the Zoom meeting. All right, so what happens if you actually get close to a black hole? And we'll talk later about what happens if I jump into a black hole. Well, let's start with something less gruesome and see if there is a wandering black hole and a star, or if there is a wandering star and it comes close enough to a black hole. If you remember what happened to a comet when it got close to Jupiter, because of tidal forces, which means it is stronger on one side than on the other of the comet got broken into pieces. In the same way, if a star got close enough to a black hole, because of tidal forces, the front side of the star would get pulled harder than the backside. Let me play this again. And so the star would actually get stretched and ripped apart by gravitational forces, by tidal forces. So that's what this video illustrates here. So you see a star that is getting close, and because of these tidal forces, it gets ripped into just gas. And that gas circles around because, you know, if there was a little bit of an orbit between the star and the black hole, it will start circling around the black hole and it will form an accretion disk. Now, this accretion disk, and we've talked about accretion disks several times in this class. For example, when stars are forming and they collapse and the central part of the star becomes a protostar, and then around it, it forms an accretion disk that continues to accumulate gas into the protostar. We also talked about accretion disks when we have a binary star where one of the stars becomes a black hole and the other one continues its life, but then some of the material from the other star starts to fall into the black hole. And this is what creates an X-ray binary, and there's an accretion disk that goes into the black hole. Well, if you get enough material going into a supermassive black hole, yeah, like in this case, if you get enough gas, you know, enough ripped stars that are falling into a supermassive black hole, then you'll get a gigantic accretion disk. And yeah, that looks like that. So this accretion disk is going to be going very, very fast, right? Because the gravity of a black hole is very large. And then as the gas spirals into, you know, the event horizon, it's going to go fast, and then it's going to have a lot of friction as it goes in with itself, right? Like sort of when you're rubbing your hands against each other, the different parts of the disk are going to be rubbing against each other. And so it's going to get very, very hot. The other thing is there's a lot of gravitational energy, what for those of you familiar with physics, what is called potential energy. And as the material is spiraling in, that gravitational energy gets converted into light, right? It gets converted into a different type of energy, which is radiative energy. And so because it's so hot and because it's converting some of this energy into light, they become extremely bright. And so sometimes these accreting supermassive black holes can be so, so bright. You know, I mean, here again, this is a galaxy. And then in the center of a galaxy, there is a supermassive black hole that normally you wouldn't be able to see. But if they are accreting enough gas, they can get these accretion disks and then become extremely bright. And sometimes they can totally outshine the galaxies where they live. This type of objects, a galaxy with a supermassive black hole in its center that is accreting or accumulating gas around them and becomes very bright, that type of object has a name. It's called active galactic nucleus, or active galactic nuclei in plural. So short for this word is AGN, active galactic nuclei. And what it is just bright, accreting supermassive black holes in the centers of galaxies. This word is very important to me because when I describe myself, like when people ask me what kind of an astronomer are you, I say I'm an AGN astronomer. That is my specialty. This is what I work on. Anyways, the reason I'm introducing AGN is not so much that I work on them, but because last year, was it last year? No, it was 2 years ago. Sorry. 2 years ago, so change that to 2 years ago. A picture of the center of an AGN was actually taken for the very first time in the history of humanity, right? So yeah, 2019, not 2020. With the pandemic, it just seems like it was last year. Anyways, in April of 2019, so 2 years ago, there's this collaboration called the Event Horizon Telescope Collaboration. It's an international collaboration with astronomers from all over the world. They make this big announcement that they have obtained for the first time the first picture ever of the light that is right outside the event horizon, right before it goes into a black hole. And so they chose a galaxy called Messier 87, and it's an AGN, right? It's one of these ones that, so this is the entire galaxy. Here you see it, and the very center is very bright. It has this jet that is coming out of the accretion disk, and there's a supermassive black hole in the center. But when you use normal telescopes, all you see is this. You see a very bright dot in the middle of a galaxy. What they did is they used radio telescopes, which they pieced together from all over the world so that they could get very high resolution. And they were able to see the very, very center of this AGN and take a picture. So it ended up by figuring out the size of the event horizon, they did the math backwards from what we did in the last class. And then they figure out that the black hole is 6.5 billion solar masses, which is crazy, right? We talked about the supermassive black hole in our galaxy. It's about 3 to 4 million solar masses. So this is 2,000 times more massive. So an incredible thing. So I have a video to play that sort of shows you how they did it, how they took the picture, and it also shows the picture. Well, the picture is this one, and that's the link to the announcement if you want to watch that in your own time. But I just have a video that explains a little more. So let me play that now.
What you are seeing is the first ever image of a black hole. Maybe it doesn't look spectacular at first, but consider this. Black holes by their very nature are invisible because their gravitational pull is so strong that not even light can escape them. So for many years, astronomers thought that an image like this was impossible. How do you take a picture of something that does not emit light? Well, it starts with a small team of innovators and ends with a telescope that is unlike anything the world has ever seen. Now, despite major advances in telescope technology, there is no single telescope on Earth that can take a picture of a black hole. They're all too small. So astronomers innovated. If one telescope couldn't do the job, then perhaps 8 would. And they were right. They used 8 radio telescopes stationed at different points across the world and kept them all in sync with powerful atomic clocks. They called the effort the Event Horizon Telescope. This series of telescopes combined has about the same capabilities as if you had built a telescope as large as our entire planet. And for the first time in history, it has shown us what a black hole around 55 million light years away looks like. This black hole is actually a supermassive black hole. It's about 6.5 billion times as massive as our sun. That's enormous even compared to other supermassive black holes, and lives in the center of the Messier 87 galaxy. And as far as experts can tell, it looks exactly like what Einstein's general theory of relativity predicted. Here's a simulation of what the Event Horizon team thought the black hole would look like. And here's the real image. The light you see here is what's called the accretion disk. It's a disk of light that forms around the black hole when a star travels too close and is broken apart in the process. But the most important part of this photo is where there is no light. That dark circle in the center, which measures 25 billion miles across. That right there is proof that black holes look and behave how astronomers thought. More specifically, that they actually have an edge. It's a place of no return, which astronomers call the event horizon. Once you cross the event horizon, the black hole's gravity is so strong that you cannot escape. Not you, nor the fastest spacecraft, and not even the fastest thing in the universe, light. That's why the edge and everything beyond it are black, trapped inside the black hole's gravitational grip. And this image may be just the beginning. The Event Horizon Telescope team has also turned its sights on another black hole, one that is closer to home, called Sagittarius A star. It's the supermassive black hole at the center of our own galaxy, the Milky Way, about 25,000 light years away. But it's significantly smaller than the one in Messier 87, so it will probably be more difficult to image. And since it took astronomers 2 years to combine and analyze data for this first image, it may be a while before we see what other black holes look like.
That is not what I meant to do. Okay. It's not responding. There. All right, so this was really, I can't even emphasize how cool this was when they announced it a couple of years ago. Let me try to get across why it was so cool. You know, we thought that we knew that there were black holes. We figure with the discovery from Andrea Ghez and Reinhard Genzel, you know, that there's a supermassive black hole in the center of our galaxy. Really, the discovery was that there was an enormous amount of mass that was concentrated in the very center of our galaxy. But is that really a black hole? And the only reason we thought, okay, it is a black hole is because we don't know of any other type of object that could have that much mass concentrated in such a small amount of space. I told you that the reason we think it's a black hole and that it goes to a very small, to an infinitely small space called a singularity. The reason why we think that is because, well, gas pressure doesn't work here, electron degeneracy pressure doesn't work, and neutron degeneracy pressure doesn't work to stop the collapse. So then we think that it just collapses to almost nothingness, right? To a singularity. But is that true? Maybe there's another type of pressure that we haven't figured out. So it could have been that there was some chunk, some thing with a very large amount of mass instead of a black hole. But if that were the case, then you wouldn't expect to see an event horizon, because the event horizon, you only expect to see it if it's an actual black hole, a place where gravity is so strong that not even light can escape. And you would not expect to see this region, like they said, like I have here in, if I can find my mouse here in this figure, this region where there is no light coming out. So they made an announcement, weeks before they actually did the press conference, and they said, we are going to announce, we're going to show this picture of the black hole. And, honestly, I was expecting it to be like like 1 pixel and not be very amazing. And I was a little nervous about it. And when they actually showed this, where you can see very clearly the accretion disk, and you can see very clearly the event horizon, And you can see how it matches the predictions that they had done with the simulations. It was really quite an exciting thing. I was joking about it, but I said, you know, it's almost a little disappointing, because it would have been so cool to find out that my entire career was studying something that didn't exist, right? If black holes don't actually exist, but they do. So I guess I'm okay. Let me see, I have a couple of questions here. Let me see if, right, so I'm getting some comments about how this didn't really look all that cool unless you understand, right? So I'm glad I took some time to this. Oh, so you can't believe that I was excluded from this project. I was not excluded. This is a radio astronomy project, right? They used radio telescopes. I don't do that. That's not my expertise. I actually work, I was going to tell you a little bit about it, but we ran out of time. The discovery that led to the Nobel Prize last year for the discovery of our supermassive black hole in the center of our galaxy, I actually worked a lot with Andrea Ghez, because I was one of the people who worked on providing the technology that allowed her to make the measurements. So I'm pretty connected to that one. But this is beyond my expertise. I do not work with radio telescopes. Someday, maybe I will, but not right now. So the black hole that they discovered, that they image, is in a different galaxy, and it's a quite distant galaxy from us. They chose this one because they knew that the supermassive black hole was very massive. And as we learned last time, the more massive the black hole, the bigger the event horizon. And they wanted like as big an event horizon as possible. So that's why they chose this one. And ironically, it's like they said in the video, it's easier to observe this one, even though it's very far away, than the one in our Milky Way, because the one in our Milky Way is a lot smaller. Right, very good. All right, so those are two: discovery of a supermassive black hole in our galaxy, the actual imaging of a black hole in a different galaxy, in an AGN. And the third discovery, this was a little longer ago, it was 5 years ago. This was the discovery of gravitational waves. This was in 2016. And again, it was like a big announcement, big press conference. I have a video about it in a couple of slides. And so the announcement that they made was that they discovered these two black holes that were circling around each other. And eventually they collided with each other and merged into one bigger black hole. Now, what did they detect? They didn't see this, they didn't take a picture. This is a completely different new way of detecting black holes. And it is by measuring the rippling that happens in space as you get two masses. So right, with one mass, you make space warp, or black holes make space get very warped. But now if you have two of these very close to each other, they actually make these ripples, like if they made waves. And it's not something that you can see, you cannot hear it, but you can detect it. If you can measure the curvature of space, which they do, and like I said, I have a video about it, then they can feel these waves that come from two black holes as they go around each other. This was very exciting too, because this was predicted by Einstein. Einstein, said, he formulated his theory of general relativity like 100 years ago, more than 100 years ago. And then all of a sudden, we're able to actually detect it. So let me show you a couple of videos, because I think they will be better than me trying to explain it.
What are gravitational waves? It all starts back in 1915 with Einstein. He hypothesized that all objects with mass would warp the fabric of space-time. If their mass is great enough, those distortions could cause other objects to fall into them. This is what we call gravity. Einstein also predicted that these distortions could travel across the universe, stretching and squeezing space and time as they move. And this is what we call gravitational waves. Later, researchers realized that if two particularly giant masses, like two black holes, are trapped in each other's gravitational field, they should start to spiral in towards each other, and so would the distortions they make to space-time. This would create gravitational waves which would travel away from the objects like ripples in a pond. But as these gravitational waves travel through space, they'd become more and more difficult to detect. In fact, Einstein thought scientists would never see them, but that hasn't stopped them from trying. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. This is a conceptually simple piece of kit that aims to measure the distortion in space-time caused by gravitational waves. LIGO works by splitting a laser beam and sending it in two directions. The beams travel precisely the same distance down long vacuum tubes. They're reflected off mirrors, and then they come back and recombine. The light waves of each laser beam are made to exactly line up so that they cancel each other out and nothing will reach the light detector at the end. But if a gravitational wave passes through, it will minutely distort space-time, changing the distance each laser beam has to travel. That will mean that the waves no longer line up. They won't cancel each other out, and the signal will be detected. The experiment is hypersensitive to disturbances, and so two identical LIGOs were built on opposite sides of the United States. Both will have to get the same reading at the same time for any signal to be considered valid. LIGO is designed to directly measure gravitational waves. This is different from another experiment based at the South Pole called BICEP-2, which made headlines back in 2014. BICEP-2 is also looking for gravitational waves, but not directly. Instead, it looks for the imprint gravitational waves would leave on the cosmic microwave background. That's the afterglow of the Big Bang. LIGO, on the other hand, is looking for much more recent gravitational waves, created only a few 100 million years ago, by something like the collision of two neutron stars or the merging of two black holes. It's been almost exactly a century since Einstein first predicted the existence of gravitational waves. And now, with LIGO, we may finally be able to tell if he was right.
All right, so this goes into a little more detail than we're covering in the class, but it is just so you know how they actually measure the waves, right? Is with this ginormous detectors that can detect very, very tiny variations in space, basically in the shape of space. Right, so let me just show you the video of the announcement.
We did it.
Thursday's announcement that astronomers have detected gravitational waves for the first time definitely got scientists excited. But it might not be obvious exactly what the discovery means. Yes, it confirms a 100-year-old prediction by Albert Einstein, but what is it good for? To see the potential, you have to know a bit about how gravitational waves work and why they're so different from everything we've used to observe the universe up to this point. Our telescopes rely on light in the broadest sense meaning electromagnetic radiation. Radio telescopes detect light in one part of the spectrum, gamma ray telescopes detect another part. There are other kinds of instruments out there like neutrino detectors, but for the most part it's all light. Gravitational waves aren't light. They're ripples in the fabric of space-time spreading out from some of the most powerful events in the universe and bringing information with them. The closest analogy is the human sense of hearing. Scientists were able to listen in as two black holes collided. The little chirps they heard are the first pieces of data from what's been dubbed new insights into how the universe works, and the same equipment has reportedly already heard several more. So a big part of the excitement surrounding the discovery of gravitational waves is that they are a new tool that can be used to discover other things. The project is already expanding too, with additional listening stations being set up in Italy and throughout Asia. For Newsy, I'm Grant Sunison.
All right. So this discovery also resulted in a Nobel Prize, and the Nobel Prize was in 2017, and 3 people who were leading the effort got the Nobel Prize. One of them, Rainer Weiss, Professor Weiss, who was actually happened to be my lab professor at MIT. Kip Thorne, we saw him in a video last time. He also was the advisor for the movie Interstellar, which we're going to be talking about a little more. So we'll see him again. And the person I wanted to focus on is the third one, Barry Barish, who was at Caltech at the time. So maybe some of you have heard the name, maybe not, but the reason why you should be familiar with him is that the year after he got the Nobel Prize, he decided to move to UCR. So he's actually one of our faculty members in our department. He's in the Department of Physics and Astronomy. And he said he moved to UCR because he saw it as a place where things were growing and where things were like, things were happening. He liked the type of students that we have. He liked, he liked it here. So he moved here. And so maybe sometimes you'll see him around campus and, say hi to him, ask him about gravitational waves. Anyways, that's why I wanted to highlight this discovery too. One of the questions that I got while we were watching the videos is there anything at the bottom of black holes? And this question comes up a lot, right? So first of all, by bottom, in the picture that I gave you before, there's the black hole, and then in the very center, it's a sphere, right? It's not a hole, and that's a problem. It looks like a hole when we're talking about general relativity because we draw things in 2 dimensions, but in reality, space is in 3 dimensions plus 1 dimension of time. So it really is a sphere, a black hole. And is there anything at the bottom, or at the center? In principle, there should be all of the mass concentrated in the very center, and that's the singularity. We'll see next class when we talk about wormholes that maybe, just maybe, there are other things like on the other side of black holes. But hold on until the next class, and then I'll talk more about that. All right, so let me do a poll just to see if you are still awake. And let me choose. This is the multiple answer. Here we go. All right, so 3 important discoveries related to black holes in recent years. A, the detection of gravitational waves as 2 black holes merged. B, the imaging of the singularity of the supermassive black hole in our own galaxy. C, the imaging of the event horizon of an accreting black hole. D, the measurement of the mass of the supermassive black hole in our galaxy. And E, the detection of a wormhole connected to a black hole. So check all that apply. It's multiple answers. I mean, 3 of these are right, 2 are wrong. So choose the 3 that you think are correct. All right, let's move on. Let me discuss the answers. So most people figured out that the last one is not correct, especially since I had just said that we don't really know if wormholes exist. So that is incorrect. A, the detection of gravitational waves. Yep, we just talked about that one. So A is correct. B is the other one that is incorrect. So B is the imaging of the singularity of the supermassive black hole in our galaxy. So by imaging, it means a picture, right? And the problem is you will never, ever be able to see a singularity. Singularity is in the very center of a black hole. It is surrounded by the event horizon. You cannot see anything that is inside the event horizon. This is part of the problem, right? That there's speculation about what there might be inside the event horizon. Some of you have asked me, like, can you actually have something that is in orbit inside the event horizon? It doesn't go all the way to the singularity. And in principle, you could, but you would never be able to see it because you cannot see inside the event horizon. Why? Because light cannot come out of the event horizon. So you can't see the singularity. You will never, ever, ever be able to see the singularity unless you actually go into the black hole. And as we'll see in a few slides, you'll probably die if you try to do that. So yeah, this is not, B is not something we expect to do ever, right? It's not just a matter of technologies. It just cannot be done. So the correct answers were A, C, and D. All right. So that's it for the exciting discoveries in the last 5 years. The next thing that we're going to talk about is what would happen to me if I fell into a black hole. And of course, we could talk about this for a long time. So I'm actually going to ask you in your homework, there are all kinds of websites and all kinds of videos that describe this, what would happen if you fall into a black hole. So I just picked one of them, and PBS has this series of videos that are choose your own adventure, right? Like you choose, are you the one who falls into the black hole, or do you push someone into the black hole? And then they let you choose different things. So in the homework, I'm going to give you instructions about which ones to watch, and then I will be asking you a few questions about them. But let's cover the main things about what happens if you were to fall into a black hole. So first of all, you have to deal with tidal gravitational forces. So we just saw what happens to a star when it gets close to a black hole. If you were to jump right into a black hole, right, same thing would happen to you. So imagine that you are this cube, and as you get closer to the black hole, the front part of you starts to feel a lot more gravity than the back part of you. I mean, they're both being attracted, but because gravity depends on distance, the part of you, like whether it's your feet or your head, if you dive in, the part of you that is closer to the black hole is going to get pulled harder than the other side of you, your feet or your other side. So it's the same as with the tides on Earth. And that's why I bothered to talk about tides at the beginning of this class, because you see it over and over again in the universe. And if you were to fall into a black hole, you would get stretched. And this has an actual term that is called spaghettification. So if you were to jump into a black hole, and as you get closer to the event horizon, you get spaghettified. And this is the actual term that you will find in textbooks and everywhere else. And why? Because you get stretched and squeezed as a spaghetti. You end up being like a spaghetti. Why not ripped apart? Yeah, you do get ripped apart, right? I mean, you get stretched, and at some point, your bonds in your body are not going to be able to to keep you together. And so eventually you're actually going to get ripped apart. And so is the pull so hard that you would die instantly? There are some funny videos about people describing, step by step what would happen to you. And, they say, well, probably you would get broken at your waist first. So at that point, you're still conscious and you're still alive, and it's just gruesome and awful, but you can still see what's happening to you. And then they talk about how, next your neck would go, and then you can still see because your brain can still process the images. Well, I don't know. I'm not a biologist, but the point is, whether it's quick or it takes longer, you probably would die. If you fall into a supermassive black hole, then you probably have a chance to actually get to the event horizon without being ripped apart yet. And why is that? Because for a supermassive black hole, the event horizon is a lot farther away from the singularity. So there's a chance that the tidal forces are not quite strong enough to kill you at that point. I mean, eventually you will die. Eventually you'll get ripped apart, but maybe, just maybe, either way, don't do it, right? All right, so as you get closer to a black hole, you feel the tidal gravitational forces. Eventually, whether it's outside of the event horizon or inside, you eventually get ripped apart. It's kind of a horrible way to die. As you approach the event horizon, objects that are behind the black hole start to look brighter and distorted. So I'll explain that on the next slide, why. But basically, if you look toward the direction of the black hole as you're falling, things will look, things around the event horizon will look distorted. As you cross the event horizon, if you look up, right, to where the event horizon is, you can still see the spaceship from to the black hole. You can still see the stars. But if there's someone outside that gave you a ride to the black hole and they stayed there, they're not going to be able to see you because you have crossed the event horizon, and so they can't see you anymore. And at that point, as far as we know, nothing can stop you. You will continue to go. You cannot go, you can't use a spaceship. You cannot do anything to be able to get you out of there. And eventually you will hit the singularity and you will become part of the black hole. Basically, you have fed the black hole. The black hole has gained your mass, and the event horizon will grow a tiny bit because you and I are not very massive at all. So we're not going to add very much to the event horizon, but we have contributed to making the black hole a little bigger, and by bigger I mean the event horizon, right? All right, so let me get to the second bullet here. As you approach, the images of faraway objects may be distorted and brighter. What do we mean by that? Well, let me introduce the concept of gravitational lenses. So when you take a lens like my glasses, right, and you put them against light, you see that light gets distorted or bent, right? So in the same way, a mass in space which has gravity can cause light to be distorted. So light is curving space, and so I froze it. And I'm frozen again. sorry guys, if this continue to happen, I will start teaching from campus. I like to teach from my home because I have a nice setup for, you know, during the pandemic, I came up with a nice setup for teaching, but teach from there. So hopefully, I think you can see me. I think I'm not frozen anymore.
Yes, we can see you.
Thank you. Right. Thank you for your patience. Like I said, if this continues, I will move my setup to my office on campus. All right, so gravitational lens is just a massive body that can bend light that is passing near it. In this case, we're talking about black holes. So a black hole can bend space, and if any light, so light likes to travel in straight lines, right? I mean, light travels in straight lines, but straight meaning following the curvature of space. Space is usually flat, so it just goes in straight lines. But if the space is curved, then light will be bent. So, for example, when we are on Earth and we're looking toward the sun, in principle, we shouldn't be able to see anything behind the sun. We shouldn't be able to see. If there was a star behind the sun, we shouldn't be able to see it. But because the sun has mass and it can bend the space around it, then the light path that should be going this way, and it should go in a straight line, and it shouldn't get to us at all. It can get bent, and then we can see it. And in fact, this was the way that Einstein proved that his theory of general relativity was correct. He made a prediction. He knew where a star was going to be. He made a prediction of where it was going to be observed, and people had to wait for an eclipse to be able to see this, and then he showed that he was correct. So a gravitational lens, meaning any big mass in the universe, distorts our view of the things behind it. So as I'm falling into a black hole, the black hole acts as a gravitational lens. And if I look at anything that is behind the black hole, then the light will be bent around it, and then it will look kind of distorted. So I know that a few of you had asked me about this, and so here is the answer. Imagine now with an AGN, right, with an accretion disk around the black hole. If you were looking at it, let me wait until there. So if you're looking at it face on, you would see it just like a disk going around an empty circle, kind of like what we saw with the Event Horizon telescope. But if you were to see it side on, you would just expect to see, again, a disk around a black sphere. But instead, you actually end up seeing something on top of the sphere and something on the bottom of the sphere. And this is due to gravitational lensing. So this is an explanation with much more details than you need to know. But the bottom line is you actually see the underside of the disk. You end up seeing it down here, and the top side, you know, gets bent. And why? It is because of the gravitational lensing. You shouldn't be able to see this part of the disk. It should be behind the black hole and the event horizon, but you do end up seeing it because the light gets bent. And so that's why you get this thing that looks so cool. So maybe you recognize where this image came from if you saw the movie Interstellar, which came out almost 10 years ago, but it's still a pretty cool movie to talk about when we talk about black holes. So next time we'll talk about just a few things about this movie, and we'll discuss which ones are right and which ones are just speculation. So have a great weekend. I will see you guys on Monday during the test. Don't forget the test. And of course, I'll stay and talk about your questions. So let me stop recording. Have a good weekend.